Hello Noddies, welcome back to our YouTube channel. Would you ever trust me if I say a single inductor can perform calculus? It sounds impossible, right? But today I will show you how one simple RL circuit can actually integrate and differentiate signals, and we will verify it using cadence simulations. So basically here integration and differentiation is in the sense if I try to give a step input, I would get the impulse if I try to differentiate it, and I would get a ramp if I try to integrate it. So let's try to design one. For the integrator part, we have to basically design a low pass filter and we have to give high frequency as input to it. And for the differentiator, we have to basically design an high pass filter and give a low frequency. Here this is the circuit for low pass filter and this is the circuit for RL high pass filter. So we know at higher frequencies inductor tends to get open circuit and the impedance of inductor is very much greater than the resistance, and at lower frequencies inductor gets short circuit and the impedance of inductor is very much lesser than R. So here the current is majorly controlled by the inductor and here the current is majorly controlled by the resistor. So here this is the equation of inductor. VL is equal to L into di by dt, and by integrating we get the equation as I is equal to 1 by L integration of V in times dt. So we know that the V out is I times R, so we are just inputting this I here to get the final equation. V out is equal to R by L integration of V in times dt, and here the current is majorly controlled by the resistance, so I is equal to V in by R, and V out is taken across the inductor, so V out is equal to VL, and VL is equal to L into d by dt times I, where I is V in by R. We get the final output as VL is equal to L by R times dV in by dt. So here we got the integration equation and here we got the differentiation equation of the inputs. So now let's try to design one. Here I am going to take the cutoff frequency as 100 Hz for the low pass filter, and here I am going to take the cutoff frequency as 100 kilohertz. My Fn would be 10 kilohertz in both the scenarios. So here this is basically a low pass filter and I am trying to give a high frequency signal as input compared to this signal, and here this is basically high pass filter and I am trying to give a low frequency signal compared to this. So I would get the final inductance as 1.59 Henry. Though the inductance value is very high, we need a much higher space for the inductor, so we tend to go for capacitance circuits. But here, since for the simulation part I am just taking it as 1.59 Henry, and here substituting this in this formula I get the inductance as 1.59 millihenry. Here for the given step input I should get the ramp signal after integration, and for the given step input I have to get impulse for differentiation. As mentioned in the previous slide, here the step input after integration gives ramp and step input after differentiation gives impulse signal. So let's try to simulate this. So open your cadence, click I to go for add instance window. Here click browse to find your analog library, and on analog library find your inductor, and from the calculation I found out my inductor to be 1.59 Henry. So I am placing my inductor, and find your resistor from the same library, and rotate your inductor by pressing R in your keyboard and clicking the component, plus W to wire your component, and press W to find your V pulse from the same analog library. Here give voltage 1 as 1 and period as 100 micro and pulse width as 50 micro. Place your V pulse and find your ground from the same analog library. Press W to finish wiring your circuits. Press check and save. Click launch ADL. Choose your analysis as strands. Give 1000 microsecond as our input is 100 microsecond for the period. Select your input and output nodes. Run your simulation. So here this is our final integrator output. Now let's try to simulate the differentiator circuit. So this is our differentiator circuit. Now the inductor is kept in parallel to the output voltage and the resistor is kept in series. So let's try to simulate this. Let me keep the trans as same and let me choose the input and output node. Click run. From here you could see we could get the impulse spike for every change in the step input. So we have successfully designed a differentiator circuit. So coming back to the expected graph, from the expected graph we could see for every step input we could see a ramp V out, and for every step input in the differentiator we could see the spike for the differentiator. So now let's try to actually add these two different circuits into one simple circuit. Now here you see this first part is the differentiator part and the second part is the integrator part. Basically here if I try to give a step input here, it should convert the step input into impulse, and the impulse after integration should converted into step input. So this is the basic ideology behind it. So now let's try to simulate this in cadence and see. So I have here rearranged the circuit. Here the first part is the differentiator part and the second part is integrator part. So here I have changed the value of inductance to. So now let's try to simulate this. Let the trans be the same. Choose your input node, output node, and also this intermediate node to check whether we get the impulse signal here. Run your analysis. So from this we could actually see for the given input step signal, I could get the impulse after the first stage, and by giving this as input to the second integrator stage, I could get back my step input. So we got our expected output. So you can try this yourself. Here basically you are going to stack two differentiator together, and here you are going to basically stack two integrator together. Try to comment down your outputs. Thank you, Noddies. We'll see you in another video.